Welcome back, everyone. We're going to repeat what we just did in the previous lecture, but with scikit-learn. We'll see that it's a lot easier, just frankly it's 1 or 2 lines of code, but we'll also see that scikit-learn offers some attributes off the fitted model that are very helpful in understanding how PCA works. So let's head back, same notebook, same data set, but now with scikit-learn. Okay, here I am at the notebook, imported NumPy, Pandas, Matplotlib, Seaborn, just loaded in the same data set as before. Note right now, it's actually not scaled. So with scikit-learn, you're still going to need to scale the data. If you want, you could set this up as a pipeline, but sometimes it's just easier to do it manually. So we're going to say import, or we'll say from, scikit-learn dot, and then we're doing pre-processing here, import the standard scaler. We'll create an instance of that standard scaler, and then we're going to scale our data. So we'll say scaled x is equal to, and whoops, let's call this scalar, so it fits with our convention. And then we're going to say scalar fit transform on df, which recall is just features. So we take a look at scaled x, and it's the scaled version. So now, graphically, if we think about that visually, everything's been shifted over, so the mean of every column is now 0. So we have our scaled x. We still need to perform standard scaling, even with scikit-learn. But let's see how much easier this is with scikit-learn. We'll say from sklearn, and it's under decomposition because you can kind of think of this as decomposing from a large feature space to a smaller one. And we're going to import PCA in all caps. If you put help on PCA, you'll notice that it's actually very simple to use. There's essentially just one thing you really got to worry about, which is the number of components you want to decompose this into. Everything else should pretty much stay the default. It's just the mathematics of how you're actually solving this. So what we're going to do here is just like before, we're going to reduce this down to 2 principal components. So I'm going to say my PCA model is equal to PCA, where the number of components is equal to 2. And then we can say PCA model, and you could technically do this in 2 steps. I could first fit the model onto my scaled x data, and then if I wanted the results, I could now take that fitted model and transform the scaled x data to go from 30 columns to 2 columns, or you could do this in 1 step. You could say PCA model fit transform, pass in scaled x, and it's both going to fit, and recall fitting is essentially just calculating the eigenvalues and eigenvectors. Transform actually does that projection step, that dot product. So that's the difference between fit and transform for PCA. One is calculating the eigenvalues, eigenvectors, that covariance matrix. Transformation actually says, okay, now take this data that you're passing in and project it onto those 2 principal components that you just discovered during the fitting process. But if you want, you could say fit transform. It does this all in 1 step. Typically, you're just going to call it fit transform if you actually want the data at the end. So we can say this as our principal components, or projected data on principal components, whatever you want to call it. So I can say PC results or something like that is equal to PCA model.fit transform. And just like before, I can then call PLT scatter, say PC results, say all the rows from column 0, PC results all the rows from column index 1, run that, and you can see we pretty much get the exact same result we got last time. It's scaled a little differently here, so that's why it kind of looks slightly different with the figure size, but it's the exact same data. So we can say PLT figure set fig size equal to what we had before, which was something like, I think 6 by 8, a little higher DPI for results looking nice, and we can see it looks good here. 6 by 8 was maybe too large. But the other thing I want to point out is we should see the same separation if I were to say C is equal to, and recall previously we had that cancer dictionary. I actually still have it loaded up in this notebook, but you can load it up the same way we did before. Recall we had this target column, which was the 0s and 1s. So if I were to color this same plot off of that, it would look exactly the same as it did last time. Okay, so pretty much the exact same results using PCA, but we could have done this with 2 lines of code. Essentially, after you're done importing it, set the number of components you want, and then call fit transform, and that's it. That's PCA of scikit-learn. Now what's really nice about scikit-learn is it has some really useful attributes, and the two most useful ones are the components themselves and then the explained variance ratio. So what we could do is if you take a look at your model, keep in mind we're looking at the model, not the results of the model. So I'm taking a look at PCA model. So we're going to say PCA model, and if you hit tab here, you'll see a bunch of stuff, but really the one we're interested right now in is the components. Note the shape here, it's 2 by 30. It's essentially explaining the principal axes in feature space. So what this actually represents is the directions of maximum variance in the data. And it's sorted based off the explained variance. If you want, you could visualize this with a heat map. It's not super intuitive information, but it is something you can further explore for the relationship between each principal component and the features that are going into it. So we could say df components is equal to pd data frame, pass in, PCA model, and then pass in the components matrix we just have here. I'm going to set the index to principal component 1, comma, principal component 2. And then finally, the columns will be equal to the columns of my original data frame. Okay, so if you run that, you can then see df composition. And again, this is showing you the directions of the maximum variance in the data. So we have the principal axes here in feature space. Not super intuitive, but it is something that's available to you in case you want to dive deeper. And sometimes what I like to do is call a heat map on this. So you can say SNS heat map, and you can even say annotation is equal to true. And this will build out a heat map for you. If you want, you should resize this so it looks a little better. You can say PLT figure, and probably a good fig size for this is equal to something like very wide, but not too tall. And let's also up the DPI here. Whoops, PLT. All right, so we have this heat map again, the principal axes in feature space, representing the directions of the maximum variance in the data. Now, what's probably much more useful is the explained variance ratio. If I take a look at PCA model again, there is explained variance and then explained variance ratio. What we're interested in is ratio because that's in terms of percentage of explained variance. So if you take a look at this, you'll see that the first principal component explains 44% of the variance in my data. The second principal component explains around 19%. So with just two components, if we take the sum of this, np.sum, two components are able to explain up to 63% of the variance in the data set. Now that may not seem like a lot, that you're losing around 40% of explained variance, but recall, if you're thinking of this as maybe a classification problem, you can see with just 60% or 63% of that variance, you're able to still separate out these classes quite well. So the question then arises is, as you increase the number of components for PCA, how does your explained variance begin to increase? So what I'm going to do here is do a little bit of a thought exercise. We will say PCA 30 is equal to an instance of PCA, where I'm going to say the number of components is equal to 30. So I'm not actually reducing anything. And then I'm going to take PCA 30, and I'm going to fit it to scaled x. No, I don't actually need to do fit transform because I don't really care about the results. I just want the PCA model with 30 components to be fitted to my scaled x data, which means I can then say PCA 30, explained variance ratio, and now I have the explained variance ratio for all 30 components that were discovered with n components equal to 30. Now, as a thought experiment, if you were to go from 30 features to 30 principal components, how much explained variance would you expect those 30 components to have? Well, we can check with np.sum, and hopefully you guessed this right, that this sum should equal 1. That makes sense because you're not reducing the data. With 30 components and 30 features, you shouldn't have to have any loss in explained variance because you have the exact same number of components or number of dimensions as before. So going from a 30-dimensional feature space to 30 principal components, you're not actually reducing the data, so you should have been able to explain 100% of that variance, or 1.0. What we can do here, though, is say explain variance as an empty list, and then say for n in range 1 through 30, create a PCA model is equal to PCA, where the number of components is equal to n. And then we can fit that model. We can say PCA fit to that scaled x data, and then take our explain variance list and append NP sum of PCA explained variance ratio. So you run that, and then we can plot out PLT plot range from 1 to 30 across the explained variances we just got, where the x label is going to be equal to the number of components, and PLT y label is going to be equal to variance explained. So you run that, and you get this sort of curve. Now, does this curve intuitively make sense? Yes, because note here, as you increase the number of components, you're going to increase the variance you're explaining. And note, we start off really high. Even with just one component, you're already starting to hit almost about a 40% marking here of explained variance. So note here, the y-axis doesn't actually start at 0. But as you increase the components, you are explaining more and more variance until you hit kind of a little above 10 number of components. You're not adding that much more explained variance. So sometimes what people like to do is use this, again, kind of as a knee graph or elbow plot to see how many number of components should I choose here. So when someone's asking you, what's the right number of components to choose, you can use, just as we've done in a lot of unsupervised learning methods, an elbow plot and decide when is your trade-off of increasing number of components, not adding too much more to the explained variance. So we can see here, somewhere between 5 and 10 components, you're really not adding that much more variance explained for adding in an entire new dimension of another principal component. Okay, that's it. I'll see you at the next lecture.